Okay, welcome to the deep dive. We're jumping into a really interesting stack of documents you sent our way, all focused on the nuts and bolts of mechanical ventilation parameters.
Yeah, some really detailed stuff in here.
We've got handouts covering core concepts like the IE ratio, different flow waveforms, and even sigh breaths.
Right.
So our goal today is to unpack these documents together, pull out the key info, and really understand what these controls tell us about fine-tuning breathing support. Let's get into it.
Sounds good. These documents really show how specific ventilation can get. It's not just about pushing air.
No, it's how and when that air gets delivered. So fundamental.
Absolutely. And right at the start, these sources talk about the IE ratio. What is that, basically?
Well, straight from the page here, it's defined as the ratio of inspiratory time to expiratory time.
So inhale time versus exhale time, the balance between the two.
Exactly. And the sources mention a typical range.
Yeah, they note it's usually kept somewhere between 1.2 and 1.4.
Meaning expiration is generally at least twice as long as inspiration, sometimes up to 4 times.
Right. Gives the lungs time to empty.
Okay. Now, what's fascinating looking at these is how many different ventilator settings can actually tweak this one ratio. What are the main ones listed?
Well, the documents list quite a few. Flow rate, inspiratory time itself, or inspiratory time percentage, respiratory rate, the tidal volume you set, and even VE, the minute ventilation. Adjusting any of these can shift that balance.
And there's this really handy table in the sources that just lays it all out.
Yeah.
Shows exactly how changing some key settings impacts I time, E time, and that final IE ratio.
Yeah, that table's great for seeing the knock-on effects.
Let's walk through a couple. What happens if you, say, increase the peak flow rate? How does that change the timing?
Okay, according to the table, increasing peak flow actually decreases the inspiratory time.
Faster flow, less time needed.
Exactly, which means you have more time left in the cycle for expiratory time, so E time increases. And the result is an increased IE ratio number, meaning expiration gets relatively longer compared to inspiration.
Okay, that makes sense. Push the air in faster, inhale is shorter, leaves more room for exhale. So decreasing the flow rate would do the opposite.
Precisely. Decreased peak flow, I time goes up, E time goes down, and the IE ratio decreases. Slower delivery takes longer.
Right. How about changing the tidal volume, the amount of air per breath?
If you increase the tidal volume, the table shows I time increases. Assuming flow stays the same, right? Takes longer to deliver more volume.
Okay.
So E time decreases because the total cycle time is fixed by the rate, and the IE ratio decreases.
Gotcha. And decreasing tidal volume?
Does the reverse. Decreases I time, increases E time, and increases the IE ratio. Less volume, quicker inhale.
Interesting how volume and flow changes can push the ratio in different directions. What about respiratory rate? Breaths per minute.
Rate is interesting. According to this table, increasing the respiratory rate doesn't actually change the inspiratory time setting itself.
Okay.
But it shortens the total cycle time. There's less time overall for each breath.
Right. Fitting more breaths into the minute.
So if I fit time is fixed and the total time shrinks, the expiratory time has to decrease.
Makes sense.
Which means the IE ratio decreases, exhale gets squeezed.
And decrease in the rate. Slower breaths per minute.
Gives you a longer total cycle time. Again, time doesn't change based on rate alone in this context, so the E time increases and the IE ratio increases, more time for exhale.
So clearly, adjusting these settings really changes the breath timing.
Yeah.
But the documents also point out something crucial. How you influence the IE ratio is different in volume ventilation versus pressure ventilation. Why is that?
Yeah, that's key. It boils down to what the ventilator is controlling primarily in each mode. In volume ventilation, you set a specific tidal volume, or VT.
You guarantee the volume.
Exactly. So the sources say here, the IE is influenced by the set rate, or that set VT, and the peak flow you choose.
Okay.
And they give formulas. Total cycle time, TCT, is 60 divided by the rate. Makes sense. Inspiratory time, I time, is the tidal volume divided by the flow rate, how long it takes to deliver that volume at that speed.
Got it.
And expiratory time, E time, is just the total time minus the inhale time, TCT minus I time. The machine figures out the time needed based on the volume and flow goals.
Okay, so in volume mode, rate, volume, flow are the big levers because they determine how much air goes in, how fast within that cycle time. How's pressure ventilation different then?
In pressure ventilation, you're not setting a target volume directly. You set a target inspiratory pressure.
And crucially,
you also directly set the inspiratory time, the I time. So the sources say here the IE ratio is influenced only by the set rate and that set I time.
Because you fixed the duration of the inhale.
Exactly. The formulas are simpler for the ratio. TCT is still 60 RR, and E time is just TCT minus the I time you dialed in. The volume delivered becomes an outcome based on the pressure, the set time, and the patient's lungs.
I see. So the direct control over I time and pressure modes makes calculating the IE ratio much more straightforward, based just on rate and I time. Different control strategy entirely.
Absolutely. Understanding which knobs control IE and which mode is fundamental based on what these sources lay out.
Okay, so moving from the timing of the breath to the actual shape of the airflow during that inhale, these documents get into flow waveforms. This feels like another level of customization. What types are described?
Yeah, it is. The sources list 4 main types: square, accelerating, decelerating, and sine waveforms.
Okay.
They basically describe the pattern of airflow speed from the start of inspiration to the end.
Let's break those down. What's the story with the square waveform?
It's a square wave. Well, it's just like it sounds. A constant steady flow rate throughout the entire inspiration.
Like turning a tap on full then off.
Pretty much. The sources suggest it might be a common starting point, maybe when you first set up the vent. The idea is the initial steady flow helps overcome resistance, and the continued flow helps distribute gas.
Makes sense.
Okay.
Consistent. What about the accelerating waveform?
Accelerating starts with a lower flow rate and then speeds up during inspiration.
Okay. Easing into it, then ramping up.
Sort of. The document suggests this pattern might improve ventilation distribution, especially if someone has, partial airway obstruction.
Interesting. And decelerating must be the opposite.
Yes, exactly. Decelerating starts with a high flow right at the beginning of the breath, and then the flow rate tapers off. It decreases as inspiration continues.
A strong start, then easing off. Any benefit there?
According to these docs, yeah, this might also help improve how the tidal volume spreads out in the lungs and potentially improve gas exchange.
Okay. And the last one, sine waveform. Sounds natural.
That's exactly what the sources say. It's considered more physiologic because the flow pattern resembles a natural, spontaneous breath. Speeds up to a peak, then slows down smoothly.
Like a curve.
Right. And like the decelerating one, the idea is this might improve ventilation distribution and gas exchange by mimicking that natural pattern.
Wow. It's pretty amazing that just changing the pattern of flow during that short inhale could potentially affect how well the air gets where it needs to go.
It really highlights the level of detail you can control. It's moving beyond just volume and pressure to really shaping the breath itself.
Yeah, tailoring it based on maybe the patient's specific lung issues.
Could be.
Okay, that brings us to the last concept these documents cover. The sigh. We all know what a sigh feels like, but what does it mean in mechanical ventilation?
Well, traditionally, as these documents explain, ventilators often had a setting for sighs. These were breaths deliberately delivered with a much larger volume than the regular breaths.
How much larger?
Typically 1.5 to 2 times the set tidal volume, and they'd happen periodically, maybe 5 to 20 times an hour. It was often just a default setting.
So like a programmed big breath every so often to pop open lung units, a regular stretch.
That was the thinking, yeah. But here's the really crucial point these documents make.
Okay.
The routine use of these sigh breaths, it's explicitly stated as no longer recommended.
Really? So that standard practice is out. That's a big shift.
It is. Shows how practice evolves based on evidence.
So if routine sighs aren't recommended, when would you use one according to these sources? Are there specific times?
Yes. They list very specific indications. Situations where a sigh, or maybe better termed a recruitment maneuver or deep inflation, is still used.
Such as?
Things like before and after suctioning the airway.
Okay.
During chest physiotherapy or CPT. During and after a bronchoscopy. Before and during extubation, taking the tube out.
Makes sense around procedures.
Also, if you're deliberately using very small tidal volumes for lung protection, a sigh might be considered then. And, importantly, during efforts to re-expand parts of the lung that have collapsed.
So it's moved from being this, automatic background thing to a very targeted tool used for specific reasons.
Exactly that. Not a default anymore, but an intervention for a particular purpose.
Okay. So looking back at what we've pulled from these sources, understanding the IE ratio and how all those settings interact.
The complexity there.
Exploring the different flow waveforms and how just the shape of delivery might matter.
Yeah, the potential impact on distribution.
And then clarifying that sighs are now for specific situations, not routine. It paints a really detailed picture.
It really does. It highlights how intricate and precisely controlled modern ventilation can be. It's way beyond just basic settings.
And for you, the listener, this shows how even seemingly small adjustments are based on pretty deep physiological understanding and have specific goals.
Yeah, it really underscores the complexity and, the ongoing refinement in critical care.
Absolutely. So considering that something is, intuitive sounding as a regular sigh isn't standard anymore.
Right, based on updated understanding.
And seeing the potential effects of just changing the flow pattern.
Yeah.
How do you think this continuous detailed digging into breathing mechanics might shape how mechanical ventilation evolves even further? That's definitely something to think about.